سلام عرض میکنم خدمت تمام دوستان عزیز که تشریف آوردن به این جلسه. امیدوارم که جلسه خوبی باشیم. میدونید این چهارمین سخنرانی از مجموعه سخنرانی‌هایی هستش که در زمینه مرزهای فیزیک توسط دانشکده فیزیک دانشگاه صنعتی شریف و انجمن فیزیک ایران برپا میشه و تا حالا سخنرانان بسیار برجسته‌ای داشتیم. این دفعه هم خوشحالیم که در خدمت استاد گروس هستیم که جایزه نوبل فیزیک سال 2004 رو دارن. استاد دانشگاه پرینستون بودن. سالها من معرفی ایشون رو به عهده آقای دکتر اردلان میذارم و خیلی خوشحالم که همین شما تشریف آوردید. من الان خواهش میکنم از آقای دکتر اردلان که جلسه رو به عهده بگیرن و آغاز کنن. فرهاد you can take on and I will disappear now.
Well, welcome to this meeting, which is a fantastic arrangement Hessam Arfai with collaboration with Kamran Wafa have established and is continuing. We hope to continue for a long time. In fact, we wish him and Kamran a long life so that this will go on for a very, very long time. It's really an honor for me to introduce to chair a meeting in which David Gross speaks. And I know that almost all of you know him very well, and you're eagerly waiting for his talk. So I won't really go into much detail, except to just mention that, to my knowledge, he's one of the most prolific theoretical physicists of our time. He has been involved in all the major developments of the last half a century in theoretical physics, even longer, since 1960s, with the matrix theory and bootstrap for the description of strong interactions. He was a student of Geoffrey Chu, who was the father of this important development. And then later on, when field theory, quantum field theory came back with full force, as you know, he's a major figure in the development of the field theory description of strong interactions, the QCD and his asymptotic freedom. And later, after the standard model has been established in 1980s, he was again a major force in the development of string theory. And after that, he has been doing things which I don't really understand anymore, developments in quantum mechanics, information theory, etc. And of course, one thing which I was quite interested in was the two-dimensional issues in holography. One of my first impressions, this is interesting, is about the start of the second revolution, the second rebirth of string theory in 1980s. I had been working in the 1970s in string theory, so after a half a decade of dark ages in Iranian science due to the revolution, when I came back and I was at ICTP with Hessam, I remembered my wife was there too also. I mentioned to people around me that this is another, this development in string theory is another fashion which will go away. And I remember him very distinctly that he was giving this smile that he's giving me now. So he knew better. The thing really stuck. And for 40 years, string theory has been with us. And he has been the major figure, as you know, the heterotic strength is due to him and his collaborators. And we have been in contact, and in various occasions, I and my colleagues have tried to have him in Iran. But because of unfortunate circumstances of the conflict between Iran and the United States, which I hope one day will go away and will be as friendly as ever, which we really deserve, all of us, Americans and Iranians. But this is the best that we could do. Now he's here virtually, and it's quite interesting that he's here when everybody else is virtually present. nowhere else you can go physically. So it's really an honor for me, and it's a challenge to have one of the greatest minds in theoretical physics share with us his words of wisdom. David, Gross, please.
Okay, well, thank you very much for the introduction. I really wish that I could give this lecture in Iran. I've been planning to come for many years now. Unfortunately, both politics and the plague are preventing it. But we hope that both of them will pass quickly. And I'll be able to visit your beautiful country, which I've never had the pleasure of visiting yet. But as soon as I can, I will. Sure. So let me share my screen and start. Let's see. Okay. Oops.
It's the matrix.
I want the window. How about that? Let's see. Okay. Hello?
Yes?
We have it.
And is this all visible to everyone?
It is to me.
It's also visible to me too. I suppose it's visible to almost everybody unless there's some problem in the internet.
Okay. So it's a pleasure to be here, although virtually. Unfortunately, I can't see the audience. This talk is really directed at the younger members of the audience and those who are not experts in fundamental physics. I'm going to cover a lot. And I'd like to start by just reminding you all that it's amazing. One advantage of getting older is that one can look back longer. And it is amazing if one looks back just 50 years, how much we have learned about physics, fundamental physics, and the universe. With the advent of quantum mechanics in the last century, we were able to understand finally the basic building blocks of all matter that we observe directly and the forces that act on them. We have also mapped just about the entire universe and reconstructed its history from the beginning, and we can imagine what might happen in the future. And with that understanding, we have acquired exquisite understanding and control of matter in all of its phases, down to the scale of atoms themselves. This has had enormous impact on our ability to control matter and, of course, therefore, on technology. But although we've learned a lot, I often like to say that the most important product of knowledge is ignorance. And by that, I mean, of course, not the ignorance that keeps our countries divided, but rather the questions at the boundary of knowledge, new questions that can be answered by observation, experiment, and theory. And it takes knowledge, it takes understanding to be able to formulate these new questions. That's why ignorance is so important. It leads to new observations, new experiments, and new things to explain by theory. So we're continually pushing the boundaries of knowledge into what I call the sea of ignorance. And that's where the frontiers of physics lie, in the boundary between what we know and what we don't know. And I'm going to discuss briefly in this talk some of the frontiers of physics, ranging over roughly 60 orders of magnitude, from the largest scale of cosmology, the structure of the universe as a whole and its history, to black holes, which are currently being directly observed and studied, as well as serving as theoretical laboratories for ideas about quantum gravity, to the structure of matter, quantum matter at the atomic scale, with applications that include the construction of computers based on principles of quantum mechanics, quantum computing. And finally, to the frontier of fundamental physics at the scale, the fundamental scale of fundamental physics, the Planck scale, which is 10 to the minus 35 meters. So from 10 to the 26 meters to 10 to the 35 meters, all in both directions, we are probing the frontiers of knowledge, the frontiers of physics. So let me start with the largest scale, the universe as a whole. And there, we actually know quite a bit. We can see what the universe looked like 400 years after the so-called Big Bang, the beginning. That is a picture that has informed us about the early history of the universe, as well as explaining how the structure of galaxies and stars emerged from a rather homogeneous gas whose small temperature and density fluctuations we see in the cosmic microwave background. We understand, or our friends in astrophysics and cosmology have explained, how that those slight inhomogeneities in this gas radiation 400,000 years after the Big Bang clumped and gave rise to this network of collapsing matter, which eventually formed galaxies and stars. And that history until now is well understood and well explained by the so-called standard model of the universe, of cosmology. We have discovered that the universe expanded rapidly at the very beginning in an inflationary period, and settled down and is currently expanding in a slightly accelerated expansion, which was discovered 2 decades ago. And remarkably, this simple theory explains in quite detail how the beautiful structure of galaxies and stars emerged from this rather homogeneous, slightly inhomogeneous gas that we see from the very beginning. However, what is still very mysterious is how the whole thing began, the so-called Big Bang. And that, of course, is where all of our equations and our understanding breaks down. One of the great frontiers now of fundamental physics is to understand the beginning of the universe. And this is not just a philosophical question, but one that directly bears on on observation. And it is necessary, we believe, to understand in greater detail what the Big Bang is in order to explain the inflation that led to the emergence of structure in the universe. How did the universe begin is one of the most fundamental questions that we're exploring. And it is difficult because it is very hard to see back beyond this gas that we observe in the microwave background. There is some hope that we would be able to probe farther back in time by observing gravitational radiation, gravitational waves that were produced in the earliest times. But that's still in the future. From the theoretical point of view, the issue is, can we determine the initial conditions of the universe? There should be, we hope, and I believe, that that's an issue for physics. We should be able to understand the principles that determine the initial condition of the universe. This is a new kind of question for physics. By and large, we don't have a theoretical understanding of initial conditions. Physics typically, given initial conditions, try to predict the future. And what does it mean to understand the beginning of the universe, the beginning of space and time? Was there a time before the Big Bang? Or did time begin at the beginning? Or is the universe cyclic? There are many ideas and speculations, but very little evidence or understanding. The other issue that we have discovered in constructing our theory of the universe is that it contains very little of the matter that we are made out of. In fact, most of the matter in the universe, dark matter, we don't observe directly, only through its gravitational interaction. And in addition, the universe as a whole is filled with what is sometimes called dark energy, vacuum energy. And that makes up currently, at this epoch of the universe, 3/4 of the energy content in the universe. So this was somewhat of a surprise when discovered experimentally, observationally, and poses very fundamental challenges to our understanding of both elementary particle physics, dark matter, and our understanding of cosmology and general relativity. So what is the nature of this dark matter and the dark energy that fill the universe? Dark matter is ordinary, perhaps, matter that interacts very weakly, but we now can directly observe dark matter through its effect, its gravitational effect. All matter attracts other matter, and we have learned that our galaxy does not just consist of the stars that we see with our eyes, but rather most of the mass of the galaxy is in the form of a halo of dark matter, which doesn't radiate and is invisible, but has a gravitational effect on the stars, and so indirectly observable. For example, here we see a picture, a reconstructed picture from lensing by astronomers of a long 60 million light year strand of dark matter in a cluster of galaxies. But we know very little about what makes up this kind of matter. We just know that it contributes to the density of mass throughout the universe, and we can map that density. But we haven't been able to see it directly. And this is one of the great challenges for elementary particle physics. Astronomers have indirectly discovered a new form of matter, but we can't see it directly. And we have been searching for annihilation. If there's any kind of matter, we believe, the fundamental principle of relativistic quantum mechanics, that there should be anti-dark matter, and dark matter can therefore annihilate and produce radiation that we might see. We also might be able to produce the dark matter directly in the laboratory. If we collide particles with high enough energy, we can produce any kind of matter. But so far, we haven't been able to find signals at the very highest energy accelerators that dark matter is produced. Another way is to detect the dark matter that exists throughout the galaxy and flows through the laboratory. Fortunately, or fortunately for us, the dark matter interacts very weakly, if at all, aside from gravitationally, with ordinary matter. So it's hard to detect, and so far, we haven't been able to detect it. But understanding the nature of dark matter, producing it in the laboratory or detecting it directly is one of the great challenges for elementary particle physics. And I'm pretty hopeful that we then begin to understand what dark matter is made of. This is one of the most sensitive experiments where we look for weakly interacting massive particles, which is one of the possibilities that dark matter is made out of, which can pass through anything very easily, and so hard to detect, and can be detected on very carefully isolated detectors like this big tank of liquid xenon. Dark energy is perhaps less mysterious in a sense because it's a natural component of Einstein's theory of general relativity. It, however, is homogeneously spread out through the whole universe. It doesn't clump. It's just the energy, if you want, of and pressure, negative pressure, of the vacuum of empty space. And it's observed only effect that can be measured and observed is that it causes an expansion of the universe. It's most matter causes the universe to not to expand, but to collapse because gravity is attractive. But the dark energy comes with negative pressure. It's a negative pressure that gives rise to this accelerated expansion of the universe. This is sometimes thought of as Einstein's cosmological constant, since Einstein realized and tried incorrectly to take advantage of the fact that in his theory, it was quite natural to have such a energy in the vacuum. He didn't like it because it was another parameter, but now we have measured that parameter and it's there and not zero, very small, but there. And it has a big effect, mostly in the future. Currently, it's causing the universe to accelerate, space to expand everywhere in accelerated fashion. But if it continues, if it doesn't decay or disappear this background energy, the universe will accelerate forever, which has a very dramatic effect on the future and the end of the universe. And that, to me, is as interesting a question as how did the universe begin? The question is, how did the universe end? How will the universe end? We might not be there to see it, but we can try to predict or understand how the universe will end. Let's now turn to a slightly smaller scale than the size of the universe or galaxies, to black holes, which were a product of Einstein's theory of gravity, although he never believed in them. They're compact, heavy clumps of matter that are so dense that light cannot escape from the so-called horizon, from the inside, interior of these black holes. And black holes have recently become a subject remarkably of direct observation, as well as they have always been and continue to be great challenges for our theoretical understanding of gravity, of general relativity. We now understand and have direct evidence that black holes are abundant throughout the universe. Every galaxy seems to have a black hole at its center, and most dramatically, in our galaxy, the Milky Way, there is a black hole, a very heavy object with a mass of 1 million times the mass of the sun. And it has been indirectly, as you can imagine, observed by mapping the trajectories of stars that go in orbits around this black hole. And then by just using Einstein equations or Newton's equations, we can determine that in the center of the galaxy there exists this black, invisible, very massive object, which we believe is a black hole. And last year's Nobel Prize in Physics was awarded to the discoverers, the astronomers who, by mapping these orbiting stars around the center of the galaxy, in a sense, discovered and observed the black hole in the center of our galaxy. But black holes are the center of every galaxy, and some of them are much more massive than our black hole, and they give rise to incredible gamma ray bursts. They're so massive that the matter around them in an accretion disk creates these jets that, with producing very high energy gamma rays that we observe. And most recently, and dramatically, the first observation of waves of gravity, waves of dynamical space-time that were predicted by Einstein's theory of gravity over 100 years ago, were observed by LIGO and attributed very convincingly to the merger of two black holes. This detection was achieved with very incredibly sensitive interference experiments in Louisiana and Washington State in the United States and in Virgo in Italy. And the first observation of gravitational radiation was well explained by the collision of two black holes, masses something like 30 to 50 masses, solar masses, which rotate around each other faster and faster and finally merge, form a bigger black hole, and then ring down. And the signal that you see here is the signal of the gravitational wave detector that observes this wave of space-time passing through the instrument, causing it to causing the arms of the interferometer to either contract or expand and change the interference pattern. Somewhat later, the same detector observed two colliding neutron stars, which collide to form a black hole. This was a very dramatic observation because the neutron stars, when they collide, produce not just gravitational waves, which were observed, but also electromagnetic radiation in all forms, from visible light to X-rays to radio waves. And after this event was observed gravitational waves, for days and weeks, other forms of light, of electromagnetic radiation, were detected. This was a remarkable observation, and it not only was, again, evidence for gravitational waves and the formations of a black hole, but also the process of these mergers of neutron stars appears to give us an explanation for the very heavy elements. So now let's go to another frontier of physics, by many orders of magnitude to the nanometer scale, to the scale of atoms. And here, 100 years after quantum mechanics, we are able to understand and manipulate and control matter at the atomic scale. And this opens up an enormously exciting area of research, to understand the various forms of ordinary matter, of atoms, but also to control them, to use them to do all sorts of wonderful things. We can, for example, create new forms of ordinary matter made out of ordinary atoms that don't exist normally in nature, such as graphene and its various applications. And one of the great hopes of this type of research is that we might be able to use some new form of matter, or just increase our control of matter we already know, to create quantum computers and keep increasing our computer power, which has, as you know, increased dramatically over the last decades, but seems to be reaching the limit given by quantum mechanics at the atomic scale. But quantum computers, in principle, if we were able to construct them, have a lot more power. Ordinary computers are based on manipulation of classical bits, zeros and ones, and that's fine. They're quite powerful. But quantum computers replace ordinary bits, just 0 and 1, by quantum bits. So a classical bit is like a spin up or spin down, but in quantum mechanics, of course, we can superimpose states of a say, a spinning particle, which either has, if measured, spin up or spin down in quantum superpositions of spin up and spin down. And that's a much larger, more powerful bit of information. And computers that are able to manipulate and such qubits are, in some cases, shown to be exponentially more powerful than classical computers and offer enormous hope for expanding our computer power in a exponential fashion. And they also can be used to simulate quantum mechanical systems that can't be simulated obviously by classical bits or classical situations. So one of the great frontiers in condensed matter physics and quantum physics currently is to try to manipulate ordinary matter to preserve the quantum mechanical coherence that would give quantum computers such incredible power. This is difficult because when these quantum bits interact with the environment, the quantum coherence is lost and the qubits become classical bits, and we lose the power. But so we have enormous prospects in condensed matter physics and in the study of ordinary quantum matter to discover and construct of matter, new phases of matter, and these prospects are extremely exciting, and perhaps the dominant, the largest number of physicists working is in this field, partly because it has so many possible applications to technology. Now let's go down another factor of a billion to the nuclear and subnuclear scale, the realm of elementary particle physics, which I've worked on for most of my career. And here, at the end of the last century, we completed the incredible standard model of elementary particle physics, theory of the basic constituents of matter and the three forces that act on them. We've discovered that ordinary nuclei, neutrons and protons, are made out of quarks, up and down and quarks, and atoms consist of electrons in rotating in the nuclei, and the electrons are accompanied by neutrinos. And most importantly, we understand the three forces that act within the atom and within nuclei. The electromagnetic force, which is responsible for the structure of atoms and governs the force between all charged particles, electrically charged particles, but also the weak and strong nuclear forces that act within the nucleus and are responsible for the confinement for the structure of nuclei in terms of quarks and for radioactivity, the weak nuclear force that flips one quark to another. This theory, the standard model, is really a fundamental theory of all the forces that we have observed directly so far. It it is unbelievably successful. To the frustration of my experimental colleagues, it perhaps is too successful. They have been testing it in literally thousands of experiments for the last 40 years in very high precision experiments carried out at very high energy colliders. And so far, no discrepancies have been observed. It really should be called the standard theory. It is a culmination of perhaps 2,000 years of a search for a theory, a fundamental theory of matter and force. Of course, it still has problems, some observational and some just theoretical. From my point of view, the most important question, open question, is how do these three forces unify? The strong nuclear force that holds quarks together is very powerful within the nucleus, but it gets weaker and weaker when observed at shorter and shorter distances. This is so-called asymptotic freedom. And if we use our very specific, well-tested theory to extrapolate how these forces look like at very short distances, remarkably, it turns out that they seem to come together at a very high energy scale, roughly 15 orders of magnitude higher than where we can currently directly observe their nature. This is a fundamental clue that these three forces, all of which, by the way, have a similar underlying structure. They all are generalizations of Maxwell's theory of electromagnetism based on a very powerful symmetry of nature. And the matter that the quarks and leptons that have the charges on which these forces act, again, are very similar. And the standard model just cries out for these forces to be unified in some way. And this extrapolation suggests that that unification occurs at extremely high energies. Of course, since we don't measure, directly observe what happens in between 10 to the 13 electron volts and 10 to the 28 electron volts, there are bound to be surprises, but this is a very strong clue for unification at a very high energy or equivalently very small distance scale. But remarkably, this scale is not too far from the scale at which gravity becomes a strong quantum force as well. Gravity is very weak at large distances, at small energies. We only notice it because gravity attracts everything. Everything gets attracted by gravity. So when we have big objects like planets or stars, they can exert a significant force. But within the atom, gravity is totally ignorable. It is weaker than the other forces, the strong, the weak, the electromagnetic, by 40 orders of magnitude. But gravity acts on energy or mass, and as we go to higher and higher energies, the force of gravity becomes stronger. And at this unification scale, gravity becomes equally important. And so again, this is a clue that all the forces of nature that we know of, the nuclear and subnuclear forces and gravity, perhaps are all unified at a very high energy or very short distance. And this has led us for many years now to explore new ways of looking at fundamental physics, in particular string theory, where particles actually have a structure. They're not just point-like particles, but excitations of an extended string-like entity. And such speculation, such ways of looking at fundamental physics have taught us that it is quite natural, this way of looking at things, for all these forces and gravity to be unified in one framework. And so, again, one of the great questions that we're exploring is, can we explain all these different particles and forces, including gravity, as different vibrations of a fundamental superstring? Super means simply that one of the ingredients of such a framework is a new strange symmetry of nature called supersymmetry, which again has not been observed, but many of us believe is there at nature at some scale and part of the fundamental understanding of the unified theory. So even starting from just trying to understand elementary particles and unification of the forces of the standard model, one is led to one of the deepest conceptual problems that has existed for 100 years, namely how theory of gravity, which is the dynamics of space and time, with quantum mechanics. And we've known for a long, long time that if we just proceed blindly and try to quantize Einstein's theory, we run into rather nasty fluctuations, quantum fluctuations of space and time at this same scale of the so-called Planck scale of 10 to the minus 33 centimeters. So if we want to understand quantum gravity, clearly we're going to have to go beyond Einstein's theory. And string theory has given us a way to do that. And it has, although it has given us examples where we can actually calculate the quantum corrections to Newton's laws of Einstein's theory, it has raised more questions, deeper conceptual questions about the very nature of space and time. Space and time are, of course, one of the most fundamental concepts of physics that we have, and our understanding of the nature of space and time has changed dramatically the last century. First with Einstein's theory of special relativity, realization that simultaneity is not guaranteed, but even more dramatically with Einstein's general relativity theory, which explained gravity in terms of the dynamics of space and time. But now we're faced with perhaps even a necessity of even more fundamental revolution in our understanding of space and time. For example, one of the things that came out of string theory was the realization that there might be more than 3 dimensions of space. Of course, we only observe 3 dimensions of space, but it could be that there are other dimensions that are curled up and are so small in their extent that we would need very high energy like accelerators or microscopes to see these other dimensions. And string theory showed us that in certain cases such more dimensions are required by the theory. So it now becomes both an observational question to determine whether space has more than 3 dimensions, as well as a theoretical possibility. In simple string theory constructions, it turns out that there are, one way of looking at it, there are actually 9 spatial dimensions, but 6 of them are curled up into little compact manifolds that are pictured here, whose structure is determined by generalizations of Einstein's equations, and have a beautiful geometry whose very structure explains some of the features of the theory of elementary particles that emerges. So again, one of the fundamental questions that we ask and try to directly observe is, are there more than 3 dimensions of space? In these string theory examples, the extra 6 dimensions determine the nature of the forces, the particular nature of the forces, the form of matter, the particular form of matter, and the values of many of the parameters, for example, in the standard model, that we so far cannot calculate. The standard model gives us no way of calculating quark and lepton masses, their mixings, and the other unknown parameters that determine these examples. All of these questions are determined by the geometry, the shape of the hidden dimensions. A very exciting possibility. I must say that when the second string revolution that was referred to in the introduction occurred, many of us hoped that string theory would give a unique or a limited set of possibilities. Unfortunately, turns out there are zillions and zillions of possible. We don't understand the principles that pick out one of these, if any, possibilities so far. In trying to understand the quantum behavior of gravity, black holes, which are now observed and studied directly in the universe, are also studied by theorists using pencil and paper in thought experiments, because black holes are cases where quantum effects can be important, indeed crucial. So a black hole is invisible classically because in classical Einstein's theory, if you have enough mass in a small enough region, the force on gravitational forces will be so strong that light cannot escape. That's why it's called a black hole. And this is fine, but it means that if you drop something into a black hole, you can lose the information carried by that object and its correlations with objects outside the black hole completely, because no signal could get out. And so this became a serious problem when Hawking observed that in quantum mechanics, if you consider the effects of quantum mechanics, black holes can actually radiate energy and disappear. So the information that is lost is actually lost completely. You can start out with ordinary matter, collapses, forms a black hole, it radiates a la Hawking, and however the information can't get out. And in quantum mechanics, one of the fundamental principles of the unitary time evolution predicted by quantum mechanics is that information is never lost. And this paradox or puzzle that Hawking revealed has led to an enormous amount of research to try to understand whether or not in quantum general relativity, quantum gravity, is information lost or not? Do we have to modify quantum mechanics? Or do we have to modify our understanding of black holes, go beyond Einstein's theory? And it appears that the answer is that we have to modify our understanding of space and time, of the dynamics of space and time, of general relativity, and that information is not lost. This understanding was made possible by one of the most important developments in fundamental physics, string theory in particular, the so-called duality between non-gravitational systems, which string theory we interpret as open strings. This is an open string vibrating. Its ends end on a so-called brane. And closed strings that are strings that are closed and whose oscillations give rise to the quanta of general relativity, the quanta of gravity, gravitons. Situation, ordinary quantum mechanical systems in ordinary space, Minkowski space, that we observe around us, the physics of such systems can be described in a dual fashion, mathematically equivalent, but dual fashion in terms of a larger space-time in which one has gravity and strings. This duality is most evident in a space-time which is a negative cosmological constant, unlike the one we observe in nature, which is positive, but a negative vacuum energy, which curves space and time so that space and time live in a box, if you want. And the boundary of that box, on the boundary of that box, we can have an ordinary quantum mechanical system with no gravity. And these are two different ways of describing exactly the same system. It's a so-called dual representation. This is a remarkably powerful way of looking at physics because we can use this duality to try to explain quantum gravity or string theory in anti-de Sitter space in terms of ordinary quantum mechanical systems, which we know very well and can control, and vice versa, to use features of string theory and general relativity in anti-de Sitter space to explain very complicated features of quantum mechanical systems in ordinary space. This has had a profound impact on our understanding of these black hole paradoxes because one can construct dual pictures of black holes using this duality. So Hawking claimed that black hole formation and evaporation would violate quantum mechanics, but one can construct quantum mechanical systems with no gravity at all, and which are completely dual to black holes in anti-de Sitter space. So, for example, a black hole in anti-de Sitter space has a dual description in terms of a close cousin of the standard model, a supersymmetric version of QCD, of theory of quarks and gluons. And the black hole, from this dual point of view, looks like a fireball that can be formed when you collide quarks and gluons together at very high energies. And in fact, such fireballs can be created in high energy accelerators at CERN, for example, and are studied directly. They, of course, don't violate quantum mechanics. They form, they evaporate, they turn into ordinary protons and neutrons and other particles, and information is not lost. So this gave us a explicit demonstration that information can be conserved using this dual description of black holes, and is now being used to try to understand in great detail how that actually happens when black holes evaporate. This duality, this way of understanding the relationship with the dual description of physics in terms of string theory and quantum gravity on the one hand, and ordinary quantum mechanical systems without gravity, has given us new insights into ordinary gauge theories, which are the basis of the standard model, offers ways of understanding string theory of QCD, for example. In quantum chromodynamics and the theory of the strong interactions, the strong force is mediated by the chromodynamic field, the field much like the electrodynamic field that couples to ordinary charges. This is the field that couples to the charges carried by quarks, the three charges carried by quarks. And it is the properties of the quantum vacuum that we discovered that lead to the lines of forces between quarks and antiquarks squeezed to flux tubes, which explains both asymptotic freedom, the free behavior of quarks at short distances, and the confinement of quarks within flux tubes at large distances. In fact, string theory itself developed before QCD was understood because of the properties of hadrons, of quark-antiquark pairs that look very much like strings experimentally. And that is always been I hear something in the background. Is everything okay?
Yes, everything is okay.
Okay, I just hearing some background noise. So I'll continue. So this duality between string theory and gauge theory has given us, as I said, benefits on both sides. And one side is to learn more about this stringy behavior of QCD, to try to calculate what goes on in at very high energies when quarks collide. But even to understand ordinary atomic physics, in the case where you have strongly correlated electrons, again, such systems can be have a dual description in terms of quantum gravity and one higher dimension. And from the other point of view, we can use our understanding of gauge theory and ordinary quantum mechanical setups to resolve some of the puzzles of quantum gravity, like the nature of black holes and the information paradox. And most excitingly, it has stimulated our ways of trying to understand space and time. Because in these dualities, one has a duality between the ordinary quantum mechanical system where space-time is rigid and fixed, and on the other side, the bulk, a theory where one has more dimensions of space-time. Space-time has emerged, that is quantum mechanical. So string theory, in many respects, this was just one of them, has suggested that many of the ways we traditionally think of space and time, space is a smooth manifold. The topology of space is fixed. You can't change topology. Certainly in classical general relativity, singularity is developed if you try to change the topology. And of course, in ordinary physics, we have a fixed number of dimensions. All of these notions are threatened by string theory. Manifold space-time geometries can change the topology, can smoothly go through what appeared to be singularities, and the number of dimensions depends on the domain physics you're looking at. Sometimes it's useful to think of 3 dimensions, sometimes it's useful to think of 9 dimensions. Space and time, and what does it emerge from? It seems clear from the existence of these dualities that one can describe physics in different ways, which are mathematically equivalent, but in which space and time appear quite different. That suggests that space and time is not as fundamental a concept as we thought, but rather is an emergent concept, an emergent way of looking at things that is good for large distances, but might break down when the distances are very small or the curvature of space and time is very big. How this occurs in detail is a subject of intensive research. Now we have these few examples where space emerges. Time is a much harder question. And if in the end we're to formulate physics without space and time, and just regard space and time as emerging, as an approximate description at large distances and low energies, what are the rules of physics without space and especially without time? Okay, I have talked for quite a while, and I'm going to end this exploration of the frontiers of physics with a short discussion as to, the future. Can we continue in this direction of exploring these frontiers, size of the universe, down to the smallest imaginable scale? Can we finish the job and answer these questions and construct a final theory? Is there a final theory of physics at the fundamental level? Are we smart enough to do that? Maybe we're just too dumb to succeed. And are we actually, are the societies, the countries that support us, will they continue to enable us to go on to construct a final theory if it exists? So is there a final theory of nature? Now, I like to pose this question in geometrical terms. I like to picture knowledge in geometrical terms. And one of the models of knowledge is what I call the onion model, which is you peel away an onion. Knowledge is an onion. You peel it away, and at the core, at the center of the onion, there's the final theory. And I don't like this picture, and it brings tears to my eyes. As I remarked at the beginning, I rather think of knowledge as a domain of what we have learned embedded in a sea of ignorance. So instead of pushing inward to the core of the onion, we're pushing outward. And this model, which one can make quite elaborate, but I won't here, is very simple, and it explains something which is a lesson you have all learned in your life, that as you know more and more and the domain of knowledge increases, you also realize that you know less and less. Ignorance, which is constrained to the surface of the domain of knowledge, increases. So it's at the surface of knowledge that we're aware of the ignorance around us. And but that only increases like the surface. And as you know, the volume increases more rapidly, at least in this geometry, than the surface. So knowledge increases, ignorance also increases. We have more and more questions about fundamental physics, but wisdom, which is sort of a ratio, also increases. So this is a good model that explains something which we all become aware of as we learn more and more. We know less and less. And to the question of a final theory. So a final theory would mean that we know everything. We run out of ignorance. So is there a final theory is really, is there a finite amount of ignorance? Now, we've had an example where there was only a finite amount of ignorance, the exploration of the Earth. This is a Eurocentric map of the Earth in the Middle Ages. The red area is what we knew, or what they knew about the geography of the Earth. Beyond that, it was ignorance. But since the Earth is round and compact, eventually we ran out of places to explore. And by now we have a final map of the Earth, at least at a scale of centimeters or meters. You can find it on Google Earth. And there is a final map of the Earth, a final. So the question in fundamental physics is the sea of ignorance compact like the Earth? Is it bounded and compact? Or is it unbounded and infinite, like a flat space, a flat Earth, where there would be an infinite amount of ignorance and knowledge could grow forever? Is it perhaps compact and finite like the surface of the Earth? In which case, at some point, we would run out of ignorance and knowledge, complete the final theory of physics. I don't know. I'm totally agnostic. It could be either way. However, there's no sign of curvature. So if we think about the history of science, so far, the more we know, the more we realize we don't know. The deeper and more interesting questions arise. So there's no sign at the moment that we're running out of ignorance. And it could very well be that the sea of knowledge is flat. I think we would realize if If it wasn't, we would begin to run out of good questions, and we're certainly not at that stage. Even if there were a finite theory, a final theory, it certainly wouldn't be the end of physics, by the way, because this kind of fundamental physics, which explores the frontiers of knowledge, is only a small part of what we do in physics. Actually, even if we're strict reductionists and there was a final theory of everything, there would be plenty of room to explore the infinite structures that we can create even with our current understanding of physics. Now, whether there's a final theory or not, it's an open question of whether we're able to understand the answers to some of the questions that we can pose today, like the beginning of the universe, the nature of space and time. These are extremely difficult questions, and we simply might be too dumb to answer them. Why should we be so arrogant to believe that our species which evolved to hunt and eat and survive, has the ability to understand the beginning of the universe or the nature of space and time? We understand that our other species, our fellow species like dogs, are not able to understand even quantum mechanics. I've been trying to teach my dog quantum mechanics, and I understand that it cannot understand quantum mechanics. Why should we be able to understand these deep questions? Again, I don't know whether or not. I think that we have certain advantages over our fellow species. And the most important one is language, whose highest form is mathematics, which has infinite capacity. As Chomsky famously pointed out, infants picking up language by listening, just listening to their parents, have the ability to utter sentences that have never been uttered before. And mathematics clearly has the same infinite capacity. Maybe not enough to answer some of these questions, but potentially at least. And experimentally, observationally, there is no sign that we're faced with questions that cannot be answered. I think if we were getting to the point where the questions we ask are too difficult for us, much like quantum mechanics is too difficult for dogs, we would begin to see that. It would be the case that young students learning physics would take longer and longer to get to the frontiers of knowledge, and there's no indication that that's happening. Young, brilliant young physicists, their early 20s, are able to get to the frontiers of knowledge and make progress into the unknown. So there's no sign that we're getting to the point where we have questions that cannot be answered. But it's possible. We could always improve ourselves, perhaps by coupling ourselves to machines or altering our genome. So I'm pretty optimistic that we could go on. The most pessimistic aspect of this, of course, is that we might lose the will and the means to continue. Our societies might not be willing to spend all the money and resources to enable us to probe the shortest distances or the largest structures in the universe. And there, again, I don't know. I certainly hope not. love to quote David Hilbert, who's on his grave, said, "We must know, we will know." So that's my hope. And with that, I will end. Thank you. Now,
Thank you so,
stop sharing.
thank you so much for such generous sharing of this unified domain of knowledge with us. I have a question. I think it's time for question, which is a little bit easier, and that is, do you think that there is the possibility in not too far a distance of formulation of a consistent string theory?
Well, I'm not sure what that means. So my view of string theory has changed over the, what is it now? It's now 53 years of string theory. I no longer regard it as different than quantum field theory. I regard the two as different aspects of the same conceptual framework that we're beginning to construct. We don't know really what this bigger framework is, but it both has stringy and quantum field theoretic aspects. But it's certainly the case that string theory by itself isn't really a theory. It's part of this framework. And one of the shortcomings of string theory was always that there wasn't a consistent known way of formulating the theory the same way that we write down the interval. But we have ways now of defining the theory, a theory, the stringy theory, or in terms of this, using this duality in terms of ordinary quantum mechanical systems, which are very much like the standard model, where we do know how to formulate it in a very precise, rigorous way. I mean, not by mathematician standards, but by physicist standards. And we can, if you want, construct solutions to the theory by using numerical techniques, lattice, QCD, for example. So yes, there are now quite, from a physicist's standpoint, rigorous ways of defining certain cases, certain quantum mechanical constructions in string theory. But the general question I have is what is the full framework of fundamental physics? And it's clearly more than just the quantum field, the limited quantum field theories that are used in the standard model. It includes string theories, but the full nature of that framework, or its full definition, is, I believe, that in the early stages of exploration, will occupy us for a little time.
So you're very optimistic, and for the young string theorists, there is hope.
Yeah, okay. No, string theory is here to stay. I mean, there's no question about that. It is. I mean, it can't, if you believe in the standard model, if you buy that, which has enormous experimental verifications, that is dual to string theory in many ways, many different ways. And so it's part of the fundamental framework. However, in physics, we have both frameworks like quantum mechanics. Quantum mechanics is part of the framework at the moment of fundamental physics. But that doesn't give us a theory. A theory is a specific set of rules and principles that allow us to make specific predictions. And string theory, so far, we've now learned is part of this framework that includes quantum field theory. But again, what we're missing are the principles that pick out a specific realization within this framework. And that we so far have failed. But I believe actually that failure is partly due to the fact that determining a principle that will pick out a specific theory is not something that physics has ever done. Standard model, there's no reason why we have the standard model. It just works. And what we're looking for now is much more than that. And it seems to me as difficult as a question as picking out the initial condition of the universe. And perhaps the two are related. Whatever theory we have that's going to emerge and therefore can be tested, given that it unifies other forces with gravity, will be a theory of space and time. And a theory of space and time had better consistently explain the beginning and perhaps the end of space and time. And that too is a question that we've never had to address in physics. So I actually believe, unfortunately, because this is so difficult that it's unlikely, I'll be unlikely to be around when we know the answer, that these two issues are related. What picked out a particular realization of this general framework that we're constructing, and what picks out a particular space-time, particular universe? I think they're related, both extremely different.
Okay, thank you. I have more questions, but I think the other people should ask. Are there any questions? Are there? Do I get a feedback?
Yes, please, if you have question, please just raise your hand. I will change the role. Then you would be able to activate your microphone and camera and ask your question. So please raise your hand if you have question.
There's somebody called Nظری who has 10 hands raised.
Oh yeah, that. But is he asking a question or is he applauding you?
Oh, okay. Applauding.
I don't see any hands raised.
No. If somebody doesn't show up soon, I'm going to ask another question.
Okay.
Please go ahead, Farad. I mean,
Okay. Going back to the early part of your talk, we have the way to observe things: electromagnetic force radiation and then gravitational radiation. Now, to go beyond this, to go to the origin of the Big Bang, I suppose you would have to go beyond the gravitons. And now, do you have any idea how that could happen?
Well, look, it's hard to understand what signals might be visible, less what one understands where they come from.
Right.
So it could very well be that there are ways of observing indirectly what happens at the beginning that we don't understand because we don't understand what happens at the beginning.
Right.
So who knows? There could be things, easy signals that we just miss because we don't know what's going on.
We have to be lucky.
But based on what we So it could be that, theory will, who knows? Theorists could understand or construct certain models of the beginning of the universe, which would say, aha, they lead to such and such, and then astronomers look under that lamppost and discover those signals. But we have no doubt, based on our current understanding of cosmology, that at the early inflationary period, there were strong gravitational effects, which lead to gravitational waves. That goes back, really to the very beginning.
Yeah.
How strong they are and what they look like depends a lot on the model. But there is hope, maybe in this century, to detect those by gravitational wave detector. You need a much larger interferometers. Or, very excitingly, if we're lucky, using pulsars, which are very precise clocks. They oscillate, and we observe their frequency of oscillation. So they're clocks, and they're spread throughout the galaxy. And a gravitational wave passing through affects their timing slightly. And so you can, using pulsars and radio astronomy, in principle, detect very large wavelength gravitational waves, which would be the kind of gravitational waves that were formed in the early inflationary period and then stretched out by inflation itself. So, yeah, there's some hope using gravity waves. Perhaps neutrinos, I don't know. But I think more likely it will be our understanding on very early stages that might suggest new ways of looking at signals. I mean, that's what happened.
Yes. There is a question here, Haniye Moradi Pasha. If she or he, I'm sorry that I can't distinguish the gender from the first name, could say it himself or herself.
Sorry, there's a question about
supersymmetry. Yeah.
Said you didn't mention anything about supersymmetry. Well, I mentioned it briefly, but yeah, supersymmetry is extremely beautiful idea, for a theorist, it's a beautiful extension of ordinary symmetries, and it's fundamentally a way we understand how to relate fermions, the kinds of particles that obey the Pauli exclusion principle that make up ordinary matter, and the quanta of forces, gluons, photons, bosons. And it's a very crucial ingredient of string theory, and it's hard to imagine that it doesn't play a role in nature somewhere. There was a lot of hope, there still is a lot of hope, by the way, that supersymmetry can explain some of the mysteries of standard model, the nature of dark matter, the so-called hierarchy, why the electroweak scale is so small compared to the Planck scale, etc. And so there's a lot of hope that supersymmetry would be discovered at the LHC, which began to collide particles at high enough energies to produce the new particles predicted by supersymmetry. That has not turned out to be the case, not at the LHC, but it's still there's a vast parameter range of supersymmetric models that are consistent with everything we know, and in which supersymmetry is at a slightly higher energy scale, and will be discovered perhaps soon. But one never knows. There's nothing in our fundamental understanding of physics that says that even if supersymmetry is an integral part of the fundamental laws of physics, that it has to show up at what, from the point of view of the fundamental scale of physics, this unification scale, is still very low energy.
If there is no one hands up to ask
Yes,
a question, I'll read something.
Yes, there are some questions. Yes.
Okay, please.
Yes, Dr. Langari. Abdullah, please. Yeah.
Okay. Thanks a lot for the...
Let me leave so that he can come on.
Okay, do you hear me?
I can hear you, I can't see you.
Okay.
Now we see you. Okay, good.
So great. Thanks a lot. That was a great talk, which I enjoyed. I myself, I'm working in condensed matter physics, but it was really a great picture of the whole as a knowledge of physics. But my question is about one of your last statement, which you mentioned that a theory, or maybe a final theory, might be to consider space and time as an emergent phenomena or emergent feature of the theory. So do we have any picture of such theories, or do we have any example of this theory?
Right, we do. In these dualities that I described are quite developed in the case of string theory or quantum gravity in anti-de Sitter space, and ordinary physics in 4 dimensions. So, one can construct, if you want, 5-dimensional space-time with gravity, dynamical space-time, out of ordinary quantum mechanical system. These are, it's now, that space and time might not be fundamental concepts is something that physicists have often considered, right? Because we don't, space and time is clearly a theoretical construct. You don't directly observe space. So it's always a way of describing things, and people used to speculate that maybe there's a granular structure. It's not continuum, it's made of something like points, lattice. These dual pictures are very different. Their dualities are situations where you can't have both descriptions valid or good descriptions at the same time. So the reconstruction is quite complex. But, you can start out from string theory. That's how it first emerged. But remarkably, it turns out condensed matter physicists trying to construct quantum states using matrix product states and so on, ended up with a, were led to a description which involved one higher dimension of space and time independent.
Right.
It works, but it's very complex, and it is highly quantum mechanical. In other words, even in this duality, the structure of space and time as described classically by Einstein as sort of a manifold whose geometry curves when you have mass and energy, emerges from the quantum properties of the dual state. So quantum mechanics plays an essential role in it. it's not easy to describe in short answer. It's very profound.
I understand, but
And
I just want to see what type of, let's say, features or let's say building blocks should be there.
Well, I give you one of the famous examples is so it relates the geometry of space and time on the one hand to the nature of a quantum state on the other hand. That's a relationship between in quantum mechanics, in a quantum state of matter, one is interested in the correlations, the quantum correlations between observables at different points in space.
Right.
So one starts with a quantum state and restricts oneself to a finite region. You lose information about what's outside that region. So you are then in a mixed state, which has a certain phenomenon entropy. In the dual state to that, it turns out that entropy is directly calculable in terms of the area of a region that extends out into the bulk from the boundary of your region and is the minimal area surface in the geometry of the bulk. So that so-called
right.
relationship relates geometry, the area of minimal surfaces in a given manifold, to the quantum entanglement of a region of space.
Exactly.
It's very beautiful and intricate. And I believe we're just beginning to explore the different ways of looking at space and time and quantum state.
Okay, thank you very much.
Sure.
Any other question?
Yes, Asal Kavand, I think.
So there's a question about what is the future of string theory? Will dark matter theory be a competitor to string theory? Well, okay. There is no dark matter theory. We don't know what dark matter is. Any theory of dark matter. There are many theories, or many speculations about what dark matter consists of and its properties. What we need now are experiments and observation. The future of string theory I tried to discuss. I believe future of string theory is very uncertain because it's really string theory is part of this general framework we have, but its future is within of this whole framework. Indeed, is to answer some of the questions that we have before us. So,
someone wanted to ask a question, right?
Yes.
Yes.
Asal Kavand and Selma Rezavand.
Is he around?
Hi,
Okay.
can you hear me?
Yes, we can hear you, but we can't see you.
Okay. Let me. I don't have accessory to. Oh, yes, I have. Okay, thank you. I can't adjust my webcam. Sorry about that. It's not a question, sir. It's just the imagination, and it's only in the imagination world. Yeah, what would happen if we imagine time like an spring, um, which when, for example, 2 points, if 2 points merge at one point in time, the space-time change breaks. Uh, what would happen if we imagine something like that? And even, for example, something like Big Bangs happened because someone fixed 2 points in one point of time, and that broke. That actually breaking of the space and time lead to that Big Bang.
I'm not sure I understood your suggestion. You know, it is. There are some cases, as I hinted at, in the case of string theory, where you can sort of understand how our notions of space and time break down. One of the great examples is when you have situations where one dimension of space is curled up like in a circle. And so you live not in, on a flat surface, but like on a cylinder. One of the directions is compact.
Mhm.
And you can imagine that circle shrinking and shrinking and shrinking. And this is a situation when you formulate string theories in such a space with a circle. That more and more, eventually you get to a point where you get a singularity. The circle becomes zero size. But in string theory, what really happens is that your description of physics in terms of this circle breaks down when the circle becomes too small. And instead, you have a different picture, a dual picture, where the circle, you also have a circle, but now it's big.
Mhm.
So the circle can, in a sense, never get too small. It shrinks and then it kind of expands again. So what happens in between can't really be described by ordinary space. It's our description. Space is just a way of describing physics. Right?
Mhm.
It's not, you don't feel space, you don't observe space. It's part of our description.
Yes.
And as you move in the description, as you change the circle, the description changes. It just becomes a better description.
Yes.
It's easy to explain in terms of functions. You could have functions which have an expansion at small values of the function of the parameter for large values, and intermediate values. You could use both descriptions, but you have to sum a lot of terms.
Mhm.
Just imagine a function of x which has an expansion for small x, expansion for large x, and they're both very good individually when x is very small or when x is very big, or when x is of order 1, you can use both, but you have to sum a lot of terms and get the same answer.
Thank
Maybe
you.
that helps you explain.
Yes.
But if you try to just push, imagine space is a real thing and you're pushing it to a singular point, you're going to run into trouble.
Uh-huh. Thank you. Thank you so much.
I think our colleague of Sharif University, Sohrab Rahbar, has a difficult question. I would like him to address it himself. Can you get on, Saurabh? Saurabh, can you hear me?
Has his hand raised.
Well, he says something here. Your idea about the topology of knowledge, etc.
Hello.
Okay, here you are. Okay, hi.
Hi. Thanks for.
Please ask the question yourself. I couldn't really understand it.
Okay. Thanks for your interesting talk, David. My question is that your idea of the topology of knowledge is very interesting for me. And we know that in the case of information, we can quantify it. We can quantify information. And then even we may define a metric for the information. I don't know. Is it possible to do the same for the knowledge, to see that if we are in the flat topology or in the curved topology? Thank you.
So I have expanded a bit on this picture of knowledge. For example, I'll get to your question in a moment, but for example, this description of the geometry of knowledge, you might ask, why is it is it simply connected, or is it connected at all? Could there be two regions? And sometimes there are, by the way, right? Sometimes somebody finds something which is disconnected completely with what we know. Often experimental discoveries seem just new and crazy. But then, of course, there's a big effort to try to connect different islands of knowledge. Although there might be disconnected regions, big effort is made and they get connected. And similarly, if the boundaries of the frontier of knowledge is very rough, if you have some ignorance which is surrounded by a lot of knowledge, it tends to get filled in. So boundaries. But to go beyond that sort of topological picture and put a metric and try to quantify is not something I've considered seriously, but it's an interesting idea. One can try to push this picture in different directions, but at some point it becomes a bit fuzzy.
Thank you.
Okay, David, thank you for understanding the question and answering it. I wonder if you can still continue with this discussion, because you probably are getting tired. Tell me how much we should go on, because people are interested in your talk and they can go on forever.
Well, let's say another 10-ish minutes.
Okay, 10 more minutes. Now, any questions?
Yes, there is a question by Selma Rezawan. You can activate your microphone and ask your question.
Hello, can you hear me?
Yes, we can hear you.
Well, I have several questions. And the first one is that I want to know your definition of time, because that's something I can just talk about it for several hours, and you know that there is no right answer for me. And the next question is that why do you think gravity is so weak? Can it be caused by other unknown or either known interaction of forces in other dimensions? And my other question is that why did all forces got separated in the very early moment after Big Bang, and why can't we see them united today? Thank you.
Well, that's a
that's a whole hour of answering.
These are all great questions. So let me start with the first about time. I don't have time to really discuss it in detail. Time, of course, is the most mysterious of things. There are many wonderful questions about time. And there's really no good definition of time in physics. It's either a parameter or a feature of a Lorentzian manifold, but it's very mysterious. For example, we all have this illusion of now, right? We exist now, and my talk was in the past, and the answer to your question is in the future. But in physics, there is no now. Where's now in the equations? So time is very mysterious in many, many ways. Then you asked, well, why is gravity so weak? It's actually a very interesting question. And there's an important discussion nowadays within framework of string theory about that gravity must be weaker than all other forces. There can't be forces that are weaker than gravity. But, you know, so at the fundamental scale, all of these strengths of forces are scale dependent. Depends on what scale you look at them. At the fundamental scale, at the Planck scale, if we believe that all the forces are unified, they're all the same strength, if you want. So then the question is, why at our scale, the scale that we live in, or the atomic scale, the nuclear scale, why is gravity so weak compared to the other forces? And that we do understand. It's because gravity, the way the strength of gravity depends on energy is quadratic. Gravity, if you want, the force of gravity is proportional to the mass or energy squared. So it grows very rapidly, like E squared, but conversely, E decreases or the lengths increase, it gets weaker and weaker. Whereas the other forces of nature, like a strong nuclear force, actually get stronger at large distances, but logarithmically. So they get stronger as we go to larger distances, and gravity gets much weaker. And the fact that gravity is 40 orders of magnitude weaker than the strong force at nuclear distances, we do understand in terms of the question, why is the mass of the proton so small compared to the mass scale of the fundamental mass scale, the Planck mass, by 20 orders of magnitude. 40 is 2 times 20. We understand that the relationship. Gravity is weak because the distance scale between the fundamental scale and the size of the nucleus or the atom is so big. It's the same phenomenon. Okay?
Thank you so much, sir. It was a pleasure to talk to you.
You had a third question.
Yeah, it was that why we don't see all forces unified today.
Why we don't see? Because we can't carry out experiments at these extremely high energies, or we can't probe at very short distances. And I think you asked whether there could be other forces that are also unified that we don't see yet. And yes, I expect there are. For example, if supersymmetry is manifest at low energies or reasonable energies, we would see other forces, supersymmetric versions of the forces we already see. So there could be many new forces, and people speculate about this all the time, in order to explain things like dark matter. However, the only thing we really have to work with that's well-grounded and experimentally tested is the standard model. And so we use that to extrapolate. And if there are other things, they can change that extrapolation, but probably not fundamentally.
Thank you so much.
Okay, the 10 minutes is over. Unless there is a very urgent question that will not allow you to sleep tonight, we can say goodbye. Is there any questions of that nature? No. Okay, David, I myself am really humbled by the extent of your knowledge, and we hope that in a not too far distant future, you will repeat this seminar. We really enjoyed it. Thank you so much.
Well, thank you for the opportunity, and it really is a pleasure to talk to you all. And I hope to see you all in Tehran in the near future.
You know, the kind of questions that you answered are usually the questions that we are not allowed to ask in classes in physics. You know, what is the nature of time, etc. It's like in our cultures in Iran, there are all kinds of questions that you are not allowed to ask. And I think in America, there is also, politically not feasible questions to ask.
Well, some of these questions, it's when I describe this picture of knowledge, when you start studying at the beginning, you have to be humble. You shouldn't ask questions at the beginning of this fundamental nature, because you have to learn a lot till you get to the frontiers. Then you're able to ask these questions.
Okay.
So one of the great motivations for young people to go into fundamental physics, which is that you then get to ask these questions.
Okay, I'm sure that you may want either to go to have your breakfast or go back to sleep. So we'll let you do that. Okay, thank you very much.
Well,
bye-bye.
Bye-bye. I thank you,
It was a pleasure.
David, as well. You increased our knowledge and you increased our wisdom in the picture you gave. Thank you very much.
See you. Hesam, could we see you, please?
Well, yes, let me turn my camera on. Yes, you can see me now.
Okay.
Good to
Well,
see you.
I say goodbye to you and thank you again. Pardon me?
And stay healthy, be well.
You too. Take care. Well, thank you very much. Bye-bye. Now, few words in Persian. دوستان عزیز، خیلی ازتون متشکرم. بسیار سخنرانی خوبی بود. امیدوارم که بتونیم این مجموعه رو بیشتر ادامه بدیم. سخنرانی بعدی ما روز 17 نوامبر خواهد بود، روز چهارشنبه. حالا جزئیاتش بعدا اعلام میکنیم که فرانک ویلچک که شاگرد آقای گروس بوده برای ما صحبت خواهد کرد.
You got that one, right?
I announced that our next speaker is Frank Wilczek in November.
Great.
Thank you very much. I say goodbye to everybody.
Bye.
Goodbye. See you soon, I hope.